Number Theory, Section 3, Congruences and Modular Arithmetic. Video 5, Euler's Theorem. In the last video, we looked at Euler's totient function phi. Euler's theorem is as follows. If a and n are coprime, then a raised to the power of phi of n is congruent to 1 mod n. So, for example, in the case n equals 6, if we wanted to know what you get when you raise 5 to the power of phi of 6, it would be 1 mod 6. And we can check that. We know that phi of 6 is 2, and so 5 squared is 25, which is congruent to 1 mod 6. Now we can use Fermat's little theorem to help understand Euler's theorem in the case where n is a prime number. So, if you remember, for p prime, we have phi of p equal to p minus 1. So if I want to know a to the phi of p, that's just going to be the same as a to the power p minus 1. And by Fermat's little theorem, I know that that is congruent to 1 mod p. Now, as with Fermat's little theorem, you don't need to know a proof of Euler's theorem, but reading through an outline proof will give you some useful insights and help you to understand it a little bit better. We're going to look at a particular example to give some sense of how the proof might work. So let's look at the example where n equals 9 and look at what happens if we take a equals 4. So first of all, I want to know what phi of 9 is. Well, if I consider the set of numbers from 1 to 9, 1 has a highest common factor of 1 with 9, 2 does, 3 doesn't, 4 does, 5 does, and 6 doesn't, 7 does, and 8 does, and 9 doesn't. So phi of 9 equals 6. I've got 6 numbers there which have an HCF of 1 with 9. Okay, let's see what happens if I multiply these by my value of a, which is 4. So I'm going to draw a little table. So I've got 1, 2, 4, 5, 7, and 8. And I'm going to multiply each of these by 4, and I'm working mod 9. So 1 times 4 is 4, 2 times 4 is 8, 4 times 4 is 16, which is 7 more than 9. 5 times 4 is 20, which is 2 more than 18. 7 times 4 is 28, which is 1 more than 27. 8 times 4 is 32, which is 5 more than 27. So mod 9, when I multiply these numbers by 4, I get the same set again, but just permuted. So if I have any value a, and I have a times 1, a times 2, a times 4, a times 5, a times 7, and a times 8. The claim is that this is just going to, mod 9, it's going to permute the numbers 1, 2, 4, 5, 7, and 8. So it will be these numbers in some order. And so that means that what I have on the left-hand side, I've got a times a times a times a times a times a. I've got a to the power of phi of 9, so a to the power of 6, multiplied by all of these things, which is then going to cancel out with what I've got on the right-hand side. So a to the power of 6 is going to be congruent to 1 mod 9. Here's that written out a little bit more neatly for you. So the numbers 1, 2, 4, 5, 7, and 8 are coprime with 9. So phi of 9 is equal to 6. And for any a, the set a, 2a, 4a, 5a, 7a, 8a gives some permutation of 1, 2, 4, 5, 7, and 8 mod 9. So when I multiply all of these together, I'm just going to get 1, 2, 4, 5, 7, and 8 mod 9. and then by dividing through by 1, 2, 4, 5, 7 and 8, I'm left that a to the 6th is congruent to 1 mod 9. This was just an example with the special case n equals 9, but the same argument can work for other numbers. You're always going to get a permutation of the set of things which are coprime with your number n. In this video, you've learned Euler's theorem and you've seen an outline of how to prove Euler's theorem.